In this video, we're going to continue our discussion on nuclear chemistry and by looking at radioactive capture. So in the previous video, we saw how nuclei of atoms can sometimes decay or emit radioactive particles or energy, like alpha particles, beta particles, and gamma rays. Well, those same types of radioactive particles can actually be taken up as well by a nucleus or captured. And the two types of radioactive particles that can be captured or taken up are beta particles and alpha particles. Our gamma rays are never going to be captured. They're only going to be emitted during radioactive decay. So the first type of capture we're going to look at is beta capture. And in beta capture, we have an atom with a nucleus with too many protons and not enough neutrons. So what's going to happen is this nucleus is actually going to take in one of its innermost electrons, combine that innermost electron with a proton to create a neutron. So when we have a positively charged proton combine with a negatively charged electron, we're going to create a neutrally charged neutron, which is going to help us balance out the number of neutrons and protons in our nucleus. And as with any nuclear reaction, we have a nuclear equation that we can use to represent it. So notice in our beta capture equation, our radioactive particle is on the reactant side. Remember, in our radioactive decay, this particle would have been on the product side. But because my beta particle is being captured, is being taken in, it's on my reactant side because it's combining with the nucleus. Also notice that again, the sums of our atomic masses are equal on the reactant and product side, and the sums of our atomic numbers are the same on our reactant and product side, and that the atomic number in the daughter nucleus is decreased by 1, while the atomic mass in the daughter nucleus remains the same. So we went from an atomic number of 4 to an atomic number of 3, so we decreased by 1, and we went from an atomic number of 7 to an atomic number of 7, so our atomic mass stayed the same. And what beta capture is going to do overall is combine this proton with an electron to form a neutron and increase the neutron to proton ratio to get our nucleus to a more stable state. So the last type of radioactive capture we're going to look at is alpha capture. And in alpha capture, we have an alpha particle, which remember is 2 protons and 2 neutrons, which is the same as the helium nucleus, which is why we represent it in this way. So we're going to have this alpha particle in alpha capture combining or being taken up by the nucleus of an atom. And this isn't going to create any new protons or neutrons. It is, however, going to cause nuclear transmutation. So we're going to go from one element to a totally different element because we're actually increasing our number of protons. So our element is going to change, which we can see down here in our nuclear reaction for alpha capture. But again, notice because it's capture, we have our alpha particle on the reactant side, and I have my parent nucleus here, and between our parent nucleus and our daughter nucleus, we notice that both our atomic mass and our atomic number are going to increase. And once again, as we've seen with all of our nuclear equations, the sum of our atomic masses is the same on the reactant and the product side. So 220 plus 4 equals 224. 87 plus 2 equals 89. And alpha capture is something that scientists can do in a lab, and it doesn't happen all that often in nature. So that's it. That's all we have for nuclear chemistry and radioactive capture. Please bring any questions you have with you to class.